So we are going to move into the next topic of forced convection. So when we discussed about convection, we said there are two types of convection. One is the forced convection, where you have a definite pressure gradient with which the fluid is flowing past a certain object, and that could be different geometries. It could be a flat plate, it could be a cylinder, it could be inside the cylinder, etc. And the other one parallel is the natural convection, which we will see after completing the forced convection topic. So here you can have two types. One is the external flows and internal flows. You can have two types. So external flow, very simple example of that is you have a flat plate. Okay, you have fluid which is flowing past this flat plate. So that's an external flow. It could be a very simple idea. So if you look at let's say a fluid which is flowing past this table, so that's like flowing past a flat plate. Okay. You could also have a cylinder. You also have a cylinder where the fluid is actually flowing perpendicular to the cylinder. That's one possibility. Okay, where the fluid is now flowing along the curved surface, of this cylinder. You could also have fluid which is actually flowing in the axial direction parallel to the curved surface of the cylinder. In fact, that's what you have in your laminar flow experiments and turbulent flow experiments, where the fluid is actually flowing past the external curved surface of the interior cylinder. Okay. Now you could have internal flows, where you could have a cylinder where you have fluid which is flowing through a tube, okay, called a pipe flow. So you can have a pipe flow where the fluid is flowing through the inside the tube, and you can have various conditions. You can have laminar conditions, you can have turbulent conditions, etc. So we are going to see these three geometries and few other simple cases we are going to see in these external and the internal flows. Okay. Now before we go into the details of this, there are two methods. So note that the objective is to find the heat transport coefficient and mass transport coefficient, local and the average. So that's what we want to find. That's the objective for all of these problems. So before we go into that, we're going to look at two possibilities. One is the empirical estimation. We're going to look at the possibility of empirical estimation, and we're going to look at the theoretical estimation. Okay. We're going to look at both these possibilities. In the empirical estimation, we're going to look at different kinds of experiments that has been performed, and based on these experiments, how to extract the heat transport and mass transport coefficient, and that will be a very small topic which we will see in the next lecture. And after that, we will go into the theoretical estimation. Note that when I say theoretical estimation, we are not always trying to find complete analytical solution. All we want is we want to find the Nusselt number and Sherwood number. So remember that Nusselt number and Sherwood number simply relates the gradient at the boundary. So if we know the gradient, we are done. So remember that Nusselt number is nothing but dt star by dx star at y star equal to 0, and similarly Sherwood number is dca star by dx star at y star equal to 0, dy star, sorry, that should be y, okay. So all we need is you only need the gradient at the boundary. So we don't need to solve everything and find the complete temperature profile and concentration profile. If we are able to find the gradient, we are good. We are able to achieve the objective of what we wanted to get. So what you are going to see is, instead of solving everything, you are going to see how to find these gradients for various kinds of problems. Okay. It's possible that in some cases you will have to solve the full equations, and you will have to generate these gradients at various properties. In some cases you may be able to find the gradients directly. So let's start with the case of a flow past flat plate. flow past fat plate. Okay, supposing there is a fluid which is flowing at u infinity velocity, and let us say the temperature is T infinity, let us say, and there is going to be a boundary layer. So, if we assume that the flow is fully developed, and it is an incompressible fluid, assume that it is an incompressible fluid, and if we also assume that it is at a steady state, okay, and not just that, if we assume that there is no acceleration, okay. In fact, if you want to maintain a steady flow, right, if you want to maintain a steady flow, then you want to maintain a constant pressure gradient, where you do not maintain there is no acceleration, okay. So, therefore, we know what the pressure gradient is, okay. So, we assume that we know dP star by dx star is known, and in fact, if we scale it out properly, you can actually maintain it at certain 0 value dP star by dx star. Note that it is a scaled pressure, okay. Now, this is if you want to maintain 0 acceleration. So, if you scale your pressure, we will come to that in a short while. So, let us assume that it is known and it is constant, and you have a fluid which is flowing at a constant velocity, okay, it is flowing at a constant velocity, and so the net acceleration and therefore the net pressure gradient, if you scale them properly, is 0. Okay. So, now we said there are two approaches. One is the empirical approach. So, we will start with the empirical approach first, and then we will move to the theoretical approach later. Okay. So, suppose, so the construction for empirical approach is, suppose I have a heating element, okay. So, let us say I know how to heat the plate. This is not a bad thing to do, it is very easy to implement this experiment, and it is connected to a power source, okay. So, I am going to heat the plate at a certain rate, okay. So, the rate at which it is heated is given by I times E, where I is the current and E is the potential difference, okay. But supposing if there is a fluid which is flowing past this flat plate at a certain velocity, okay. Now, at steady state, you expect that we should maintain the temperature of the flat plate, okay. So, let us say that the temperature of the flat plate is maintained at Ts. So, the amount of heat that is supplied to the flat plate is controlled in such a way that the temperature of the flat plate is maintained at temperature Ts, okay. So, therefore, the amount of heat that is transferred from the plate to the fluid at steady state is given by H into whatever is the surface area of heat transport multiplied by the temperature gradient. So, this H should be average or local. Yeah, it should be average, because what the amount of heat that you are supplying here is the total amount of heat that is supplied to the plate. So, if you want to look at the total amount of heat that is transferred from the plate to the fluid, you should actually use the average heat transport coefficient, okay. Then that should be equal to I times E. So, that is not difficult to see that, okay. So, from here experimentally one could estimate H bar. So, if I put a subscript L, if L is the length of the plate, so if I say this is average heat transport coefficient based on the length of the plate, so HL would be I times E divided by Ts minus T infinity. Fair enough. So, we know how to calculate the heat transport coefficient experimentally. Now, so we said that the functional form in the Chiltern-Colburn analogy, we said the JH factor is Stanton number multiplied by Prandtl to the power of 2 by 3, right. So from here one could guess that the Nusselt number should be a function of Reynolds number and Prandtl number, okay. So of course one could guess that the exponent that you will get PR to the power of n, right. So that exponent should actually be 1 by 3, we could guess from this Chiltern-Colburn analogy. But then let us assume that there is a general functional form. So I am doing an experiment, there is no reason why I should assume that there is a certain functional form, okay. So if there is a certain functional form, it should actually come out of the experiments. So remember that anytime you write a model or you conduct an experiment, it's always better to start with assuming nothing. Excuse me? Yeah, this should be the average, right. So, because that's what we are going to measure. So it's better to start with assuming nothing. So let's say we don't know what this functional form is, and can we detect it from the experiments? And the answer is yes, you can. So although it's not a very correct thing to say that the person who did the experiments and found the functional form did it without any basis, that's not correct actually. So he has actually done the analytical theoretical approach and found out what should be the correct way to plot these data. So remember, you will not be able to get the functional form until you know that Nusselt number and Prandtl number are important, right. So what they would have done is they would have first made a plot of Nusselt number versus Reynolds number, okay, at various Prandtl numbers. Various Prandtl number values. So note that Prandtl number is the property of the fluid. So if you can change the fluid, you conduct the experiments with different fluids or different temperatures, where you are now able to control the thermal diffusivity and the momentum diffusivity of the fluid. So you can repeat these experiments n number of times. And so what they did was they made a plot of log of this average Nusselt number. So note that average Nusselt number is HL bar into the length of the plate divided by Kf, the conductivity of the fluid, okay. So you know Kf, you know the length, and you know the average heat transport coefficient from your experiments, and you know the Reynolds number of the flow. So it's not by chance that they found you have to plot log, it's actually some of these theoretical Colburn analogy was used to understand what should be the functional form that you have to use to extract information from this data, okay. So they made a plot for different values of Prandtl number, PR1, PR2, etc., different values of Prandtl number, okay. And then what was done was they found that there is some correlation between Reynolds number and Prandtl number. So then the next stage was they said, okay, let's try to look at log of Nusselt number by PR to the power of n, we still don't know what the exponent is, okay, and log of Reynolds number, okay, Reynolds number to the power of m. So let's try to make a plot, because they got some insight from the Chiltern-Colburn analogy, okay, and they made a plot of this sort, and then you get some sort of a straight line relationship. So note that this was done 100 years ago, more than 100 years ago. And so in those days, you know, getting a straight line plot is like a bingo. They always want to see what can we do so that you can get things towards a straight line. They never had Excel, okay. Excel was, the concept of Excel itself did not exist in those days. So, and concept of computer itself did not exist. So they, whatever solutions they made, whatever problems they looked at, they want to try to bring it to a form which can be fit manually by using your hand calculation. So they try to bring it to the straight line form, not by assuming anything, but by looking at the functional form that one would get using the Chiltern-Colburn analogy. So then, therefore, they found that should be some constant c multiplied by power m and Prandtl to the power of n. So now the exercise is just to find out what these constants c, m and n are. Okay. So from the experimental data, if you have statistically enough number of data, so one could always question what is meant by statistically enough, but let us assume that we know what is statistically enough number. So if you have enough amount of data, you should be able to calculate c, m and n. Okay. It's a very boring task, but somebody has done this boring task. It's like, you keep a plate, you put a fluid, run it, measure this, put another fluid, change the temperature, measure it. It's a very boring thing to do, okay. But somebody has done it for us, and we are not going to do this, and I don't think such kind of an experiment any of you will be doing ever. So people have done all these things. In fact, people have done this for different kinds of geometries. But what is more interesting is to look at what are the different theoretical approaches. Yes, it does. Yes, it does. Except that these experiments are different. Yes, it does. And in fact, you will see that for different kinds of geometries is a very, very similar functional form that you will see whether it is external or internal flow. An excellent example of that is those who have done laminar and turbulent flow experiments. You will see this functional form that is given to you for both external flows and internal flows. Whether it is flow through a tube, whether it is flow past a tube, flow past a flat plate, whatever kind of, so it's a pretty ubiquitous functional form that you will see in all kinds of geometries. And the reason why it is ubiquitous is because of Chilton-Corbin analogy. We didn't assume, look, we only said that it's a flat plate, but if let's say if it is cylinder, instead of having a Laplacian and Cartesian coordinates, you're going to have a Laplacian and cylindrical coordinates. But so what? The functional form still remains the same. In fact, when we made this analogy, it's a very general analogy which is valid for pretty much all the geometries that you can think of. So what is more interesting for the course purpose is the theoretical approach, although you must know what the empirical approach that was used in order to verify some of the theoretical predictions. So hereafter what we will see by and large is going to be the theoretical approach that has been used. And what is important to also note is that the equations that you got, the governing equations that you got earlier, they were all nonlinear. So note that the temperature and the concentration equation, they were nonlinear because it has both temperature and also the velocity function. So it's not a linear equation, and not always you will be able to find analytical solutions. Unlike what we have seen in most of the course, you will not be able to find analytical solutions for all the model equations that you would be writing hereafter. That doesn't mean that you cannot get insights into what's happening. You will still be able to make some approximate solutions. So note that these things were done several decades ago when computers did not exist. So there were some innovative ways of finding solutions. For example, series polynomial solution is one. So people had looked at different methods and solved these nonlinear problems using different mathematical techniques. And of course, now you could always go and brute force solve it in MATLAB or any other computer software, and you should be able to find similar solutions. Okay. Now, what is also important to note is that the objective. So remember that the question that we are trying to ask in all of these problems is, what is the average heat transport coefficient? What is the average mass transport coefficient? So we really do not need the full temperature profile and full concentration profile. We have it, good, well and good, but that's not really important. What is important is only the average, and this depends only on the temperature gradient at the boundary and the concentration gradient at the boundary. So if we are able to find these two quantities for a given problem, we are done. So the methods that people have developed, series solutions, etc., they concentrated on finding these two quantities for any kind of geometry that one was interested in.